So I'll talk to you about how to use hacks for correct and secure zero-knowledge implementations. So first, the question we want to help answer is, can we actually trust online voting? And how do we actually ensure that the security of online voting is implemented by some smart contract? And in this regard, there is also some push to do more high assurance. So there is some EU Data Act about smart contracts. One of the subsections of this act is about robustness and access control, which states that you have to ensure that the smart contracts have been designed to offer a high degree of robustness to avoid functional errors and to withstand manipulation by third parties. And our goal is to show that you can actually do formal verification to get this high assurance, and thereby make formal verification one of the standards for getting high assurance and implementing protocols where it's very critical that they're doing the right thing and are robust, for example, for smart contracts. Another example of this is also the Swiss e-voting regulation, which states that you have to have some form of formal security proof in the computational model for things you do for voting. So another question could be, why is voting even relevant, and also specifically, why is it relevant for blockchains? So voting is used many places inside of blockchains. It's used for consensus, governance, and decentralized organization. Furthermore, the adversarial model inside of blockchains is also very complex. So looking at cases for using these security proofs in the context of smart contracts is also very interesting, because we are working with a very strong adversary, and we can therefore show that we can also have strong adversarial modeling and still get usable results. Furthermore, just in general for voting, the stakes are very high, both societal but also in a financial sense. When working with blockchains, there's a lot of transactions going on, so investing a bit in getting the correctness of your implementations is very relevant and can save a lot of money in that way. And issues in this can be that there can be bugs in both in the specification. So you could have written something where you were imprecise in how exactly you should implement something, and some interpretation of the specification might be wrong. You could have been incorrect in your cryptographic proof on paper. You could have written something wrong, or you had some detail you forgot. Or it could be in the implementation, you implement something that doesn't follow the actual specification. Yes, so our process to try to alleviate these problems is to use hacks for writing the specification. So hacks is a framework where for implementing these things, it's done in a safe subset of Rust. The idea is here you can implement the specifications as a runnable specification, and then it has translations to a lot of different backends. So we have some proof framework backends. So we have RUC as one, F* is also another, and ProRef is a third. And this framework is very general and encourages a lot of like cross theorem prover, cross tooling interaction. So you could add, for example, Lean as another backend without having to do too much to get there. We then take these things, and for our case, we translate it into RUC. Inside of RUC, we have a security library called SSProve, where we prove some security properties about this smart contract, this voting protocol. And then we also use Concert to prove functional correctness of the smart contract and prove some trace properties. And then finally, you can take all these proofs on the code, and you can re-extract the code. And you can take some of the re-extracted code and replace some of the elements with more efficient implementation, where we have the libcrux library, which has secure, verified, fast implementations. Yes. So more about hacks. So as I said, hacks is a subset of safe Rust with translations to proof assistance. One of the projects within HACS is HACSpec, which has a goal of making a lot of these internet standards like IETF and NIST more machine readable, so we can actually run them and we can have reference implementations to test against. Even though they might not be efficient implementation, they'll still allow you to do a lot of proofs of correctness on the specification itself and allow you to have a concrete definition of what the specification is and alleviate some of the bugs that can be in the specification itself. Yes, and as I say, HACS is a subset of Rust, so you can also actually just run the specification. Here we can take elements of the specification and replace them with efficient parts that we know are secure. So if you have a specification that uses some curve, we can have an efficient implementation of that curve instead of the more high-level specification. Yes. Now for our next tool is SSProof. So SSProof is a tool we use to do modular proofs of cryptography. It's a library within RUC. It's a formal way of doing state-separating proofs. And the language inside of SSProof is a magnetic state and probability-based language. Furthermore, we have a program logic within SSProof to do reasoning about equalities of programs and manipulation of programs. And that is derived from the categorical Dijkstra-Monad framework. The way you do proofs within SSProof is this game hopping style of proofs in the computational model. And SSProof also has a large library of useful examples. So since it's so modular, you can take protocols or primitives and prove them secure and reuse those proofs and guarantees in larger protocols. Some examples are, we have a lot of the joy of crypto formalized in SSProof. Next we have Concert. So Concert is a framework again in RUC for doing smart contract certification. The concrete way that Concert works is that it models an abstract account-based blockchain with pure smart contracts. So here we're not working with a lot of state-based things, but a lot of existing blockchain frameworks are also working with functional code. So having this model is not that much of a restriction for actually doing the reasoning we are working on. And we also have some verified compilation to a lot of targets. So when you want to re-extract the smart contract you have verified here, you can extract it to, for example, WASM, but also Rust, Haskell, OCaml, C, and other targets are possible. Now, coming back to our case, is a case of online voting. So more specifically, we're looking at the Open Vote Network Protocol, OVN. The parts in OVN for we're doing security proofs of a commitment scheme and 2 zero-knowledge proofs. The OVN protocol is quite simple. However, many of the parts are parts you would also use in like larger protocols. So OVN is made for doing boardroom voting, which means that it's voting with like 50 to 100 people or something, but not like large-scale elections. However, you could imagine reusing a lot of these components to prove something like election guard, which is a larger effort for doing actual large-scale votes. Yes. As many of you would know, zero-knowledge proofs are a big part of this. So the zero-knowledge proofs we are using in this this work are the Schnorr protocol and an all proof for showing whether the vote is a 0 or 1, but not revealing which case. And we are also working a lot with Sigma protocols. So both of these zero-knowledge proofs fall in the category of Sigma protocols. In SSProof, we have a framework for reasoning about these Sigma protocols. So we can show the security properties of these Sigma protocols by showing the correctness of the protocol by doing computation in SSProof. We can show special honest verifier zero knowledge by defining a simulator that can construct the transcript given just the the response and the challenge. And finally, we have shown simulation sound extractability, where you construct an extractor that, given 2 valid runs for the same witness, gives back the actual input. And having these 3 properties ensures the security of the Sigma protocols we're using, and we have shown these for both the Schnorr protocol and the OR protocol we use in the in.
You mean special sound extractor? It's not simulations. When you extract from 2 runs, it's called special soundings?
So I think this is a stronger guarantee where simulation, but yeah, maybe. Yeah. And as for the protocol in general, so the way the protocol is structured is in 4 different rounds. So in the first round, everyone commits to a public key and publishes the public key on the blockchain. In the second round, everyone checks the commitment and compute a commitment to their vote. In the third round, everyone shows that their vote is either a 0 or 1 and cast their vote. And in the final and fourth round, everyone just validates all the commitments and tally the result. So the protocol is built up in a way where the final result is just a combination of all the parts given, and you end up with it just being the result is in the exponent, so you just brute force the exponent, which is also right. This protocol is not fit for large-scale things, because you would have to brute force an exponent for a very large number if you have like larger elections. The reason here we have round 2 and round 3 being separate instead of just casting the vote and committing to it. The reason we actually have introduced this commitment is that otherwise you would be able to look at how others cast their vote and have that influence how you cast your vote yourself. So therefore we have an extra round with this commitment. There exists a version of this protocol where that is not a thing. Yes, and the properties we want for the full protocol are these 3 top properties. So you want self-tallying, which means that anyone can like audit the result and just tally the votes themselves. This is part of us just publishing the result. It might be hard to do this because you have to brute force this exponent, so it might not be something you want to spend the money to compute, but it is possible to do, and therefore it's also important to have this auditing step for voting protocols. The next property we have is maximum ballot secrecy, which means that you can actually not see what people are voting given the result. So all the ballots are indistinguishable from just some random input, which is the security property we want. And finally, you have universal verifiability, which again has some ordering properties, so anyone can verify that the protocol was actually done correctly, so the run of the protocol was done correctly. And this boils down to the zero-knowledge proofs, so having that everyone can validate that both the commitments and the zero-knowledge proofs done throughout the protocol are correct, ensures that we can't change the input, we can't vote 2 instead of 0 or 1 or something like that. Yes. And as I say, the security properties are given for the commitment scheme, and these zero-knowledge proofs are given in SS proof, and the functional correctness we have shown in concert. Yeah, so we can look at how this actually looks in SS proof. So here I've written up the protocol and the game jumps we're gonna do. So this is the proof of the maximum ballot secrecy, so showing that we cannot distinguish the input vote from just random noise. So the idea is we basically try to push the secret key sampling all the way through the protocol by step idealizing different parts. So the first step up here is idealizing the discrete lock assumption we have. Next up, the second part is idealizing the Schnorr protocol. The third jump is then we want to idealize again another use of the discrete lock. Fourth step is idealizing the OR protocol, the CDS protocol. And lastly, we can just push it all the way through the tally, which means that we now idealized the entire protocol and shown that we are not actually depending on the input anymore. So no matter what input the user gives, we can show that it's equivalent to a program where the input is just random, so we can distinguish the output of the two programs. Yes. And now for some related work. So instead of doing this verification in SSProof, you could also look at tools like EasyCrypt. The difference between SSProof and EasyCrypt is that EasyCrypt is not a foundational framework, whereas SSProof is a foundational framework, and SSProof is in the context of the ROC ecosystem, so we have some tools there to help with some things. Then we also have some other projects, some of which are unmaintained. So there's Certicrypt and the foundational cryptographic framework FTF and Cryptol, which we heard about a bit earlier. There are also some other styles of provers. So there's some symbolic provers instead of computational. One of these is also present as a backend for Hex. So ProVerif is an existing backend for the Hex framework. Squirrel and Tamarin are other symbolic provers, which could possibly also be added to the Hex framework. And as I mentioned earlier, an alternative voting protocol, which might be more realistic, is the election guard protocol. But for that, there's a bit more off-chain parts, but a lot of the other building blocks are the same. So you'd have to do a bit more reasoning, but the general structure would be the same as what we've done for the OVN protocol. So in conclusion, we have a formalization and an implementation of a zero-knowledge proof, or protocols using zero-knowledge proofs as part of this OVN protocol. This is the first time showing both the correctness and security of some smart contract, and it illustrates possibilities for using formal methods as a requirement for online voting, and trying to push this high assurance also could mean doing actual proofs by creating the tools that makes it easier for everyone to work with proofs and defining proofs. And all of this can actually be made efficient and can run efficiently using the libcrux library for verified cryptographic primitives. Thank you.
Any questions?
I just have an answer to your question from earlier. Simulation sound extractability is just exactly the same thing we call simulation extractability. It was defined by Jens Grott it's an AsiaCrypt 2006 paper. Simulation sound is K-proofs for practical language with constant size group signatures. Just to clear that up.
Anyone else?
Okay. Maybe lunch then. Thanks
Yes.
for the great talk.